Welcome to another RDWorks Learning Lab. Now, much as I anticipated, there were a few people who did not fully understand my theory of cutting with lenses. So I'm just going to very quickly go through with a modified diagram of how now I, in my mind, see lenses operating. And I hope that will clear up exactly what I'm trying to propose. Now we'll then go out into the workshop and do some more test work that I've thought about, but I've done no preparation for, just as normal. So we'll just fly by the seat of our pants and see what happens. This is a journey of exploration for me. This is not a teaching session, as some people still think that I'm doing. I don't know the answers. I'm hoping to prove some of the stuff that I'm theorising on. And here's a health warning. It may offend some of the purists when you see some of the things that I think I'm going to be doing. Well, here is now the image that I carry in my mind of how lenses work. Previously, it had just been light rays that crossed over at the focal point, maybe not exactly at the focal point, because as I said last time, there is a sort of a slight variation in the focus depending on whether the ray's coming from the inside or the outside. Right? That's called spherical aberration. But this is an extreme version of spherical aberration in red that I've drawn on here. So instead of the rays diverging below the focal point, this very special set of rays here, which are grossly exaggerated, very close to the axis, which I've missed out because the axis is only going to add confusion to the situation. And I'm saying that this band of light either side of the axis is so close to the axis, and this surface of the lens is so relatively flat, such that the focal point actually doesn't happen here. The focal point happens here, way below the nominal focal point. Okay, now as we change the shape of the lens top surface, the convex surface, this amount of curvature that allowed this to happen is happening over a much smaller distance away from the center line, because the curvature is falling away at a different rate than it is here. Here it's very slow, and here it's getting a bit faster. So for the same amount of flatness, and I hesitate to use that word because some people misinterpret that, but this area of flatness here over which this zone can exist, that same flatness exists over a much smaller zone. Basically the spherical diameter gets smaller, but the curvature effectively gets greater. Now I think I previously defined this as a hole in the lens, and people took that too literally. I really mean this as a property weakness of the lens that doesn't conform to the requirements of focusing the lens into a fixed position. This is so close to center that it defies the rules, and the focal point projects way out here. Now, as I said, when we start changing the shape of the lens, the focal point changes. As you can see, it's a much shorter focal point than that one, because that's a shorter focus lens. And then we would go to even shorter focus lens, and we get an even shorter projected focal point down here. And this band here is narrower again, because the flatness area is even smaller. So with the 1.5 inch lens, this area of, as I said, I'm reluctant to keep using this word flatness, but it's the best way that I can describe it. Through this little area of weakness here gets much smaller because the curvature is greater. And so therefore the lens focuses much quicker because of the curvature. But these rays are still here. You cannot ever get rid of this weakness, no matter how short you make the focal length, because there is always a single beam which passes through the axis which goes to infinity, and then a very short distance away from that axis, those crossing light rays will come in from infinity quicker and quicker depending on the shape of the lens. And here we've got a very short projected focus, and as the lens gets longer, so the projected focus gets longer, which is why you can cut deeper with a longer focus lens. You can't cut this 26mm thick material with a 1.5-inch lens. You wouldn't normally expect to cut this 26mm thick material even with a 2.5-inch lens, because you just wouldn't think that a 2.5-inch lens had got a long enough projection. But in fact, this 2.5-inch lens that I cut this with is a gallium arsenide lens, and it's even flatter than this. So it's almost like a 5-inch lens because of its flatness, and because of its flatness and geometry, it has a huge projection beyond the focal point. Hence, it can cut much deeper than you would normally expect a 2.5-inch zinc selenide lens to cut. That basically sums up what I was trying to describe to you in the last session. So when I was speaking to Steve at APC recently, I asked him about this diagram here. And so look, you can see that the rays are crossing over, and we've got this nominal focal point, this theoretical focal point. What's this bit here? The blue line. He said, well, that's a projection of where there are photons. Yeah, what does that mean? They're escaping? Does that mean light is not travelling in straight lines? Look, we've got green rays which are coming down here to a 0 point, and then we've got these red rays which are in fact not coming into a 0 point here. They're not coming into a 0 point till down here, and so consequently they are outside the normal crossover focal point. And if we look here, we would say, well, hang on, yeah, we have got photons here. Look, they're all the way here, and then they come out down here. Is this the reason why people are always drawing this with a wasted shape rather than a crossover shape? But it's a possible explanation as to why there are photons in the area that you wouldn't normally expect photons. But hey, as I mentioned to somebody else in a comment, I don't think any manufacturer of lenses is going to admit to the fact that they've got something like this happening in their lens, because they're trying to produce the most perfect lens possible with everything passing through the focal point. Any failure to pass through the focal point is basically admission of spherical aberration, and they do everything in their power not to have spherical aberration. In fact, there are special lenses around which we cannot get hold of for our machines because they're just stupidly expensive if you were to order them specially, and they're certainly not commercially available, and they're called aspheric lenses. They're like a mixture of a 4-inch lens and a 1.5-inch lens. So we've got a little bit at the centre here, which is like this radius, and then we get all sorts of funny shapes around the outside of this centre section here, trying to make sure that we don't get any of this spherical aberration and we get perfect focus at a single point. They're very expensive lenses which I suspect would do wonderfully well for engraving. But hang on, if this is what we need for cutting, it sounds as though they're going to be crap for cutting. I don't know, because I'm not going to be able to get one to play with. So today what we're going to try and do is to see if we can find a way of proving this little point here, that something is happening right close to the axis of the lens which gives us cutting properties. Now we already know that the cutting properties decrease as we change the focal distance, because with a compound lens, for example, you've seen some of my penetration results. They're not very good at all, and that's because the focal distance is actually so short. There is still some cutting ability. As I said, no matter how short, how perfect the focal length of the lens is, there will always be this weakness through the axis of the lens. Even in an aspheric lens, it will still be there, but it may well be very, very short, because it's going to be like this 1.5-inch or even a 1-inch lens or even a compound lens. Well, we're going to start off by repeating our cutting of 26mm oak with the 2.5-inch gallium arsenide lens. It's a plano convex lens, flat sided. Say that probably looks like about a 0.5, maybe 0.6 wide kerf. I think there's a few little stringers along the bottom that are holding it. Just a few little tags along there, look. Now the reason why I want to do that is because I'm now going to change things very slightly. I've got a piece of 3mm MDF here. I'm going to add that to the stack. Now I'm not going to stupidly cut through that as well. Set that to the same focus as it was before, 2mm above the surface, and then I'm going to remove the piece of wood. We'll see what the power looks like at the bottom surface of this wood without the kerf to contain it. Obviously there's obviously got to be a lot of power to cut through 26mm oak, so there's going to be still a lot of residual power that I expect to find on this surface here. Yes. Okay, now what we're going to try and do now is to filter out some of that power by putting the speed up. I can see clearly in there that the centre, and you saw the very, very bright white light, which was basically the carbon arc in the middle there, it's burnt its way right through, and yeah, we've got obviously scorching around the outside and a very deep centre to that groove, but it is a very wide groove. What, 4mm wide? So let's change the speed from 3mm a second up to 53mm a second. You can't really probably see that because there's no 3D on this camera. There is a very distinct deep groove V in there, indicating that we've still got a lot of power in the centre of that beam. Not near the centre of the beam, but right at the centre of the beam. So I now push the speed up to 100mm a second. Several things you can note. First of all, the colour is changing from dark to much lighter, so we're spreading out the power. The exposure time is less, so we're doing less burning. But you'll also notice that very thin line right along the bottom of the groove again. It's still there. We've got a thinner line, so we're gradually filtering out all the extraneous low power that we don't need. But bearing in mind, this is the bottom of a 26mm cut, and we've still got power right down the centre of that beam. I think we're definitely on the right track here, because according to lens theory, the beam is diverging, and so there cannot be any concentrated power right at the centre of the beam. Certainly not 26mm below the focal point. Now this time we've got a 4-inch zinc selenide lens tucked in the top of that lens tube. So that's 1mm. Is can we find the thinnest line? You could say they're either all quite thick or they're all quite thin. They're all the same basically. That one's definitely not in, so that's 1. So anything between 2 and 8. Difference between 2 and 8, well, let's choose that one there, which is 6. So that's 7mm below the nozzle. 7mm below the nozzle. I don't like working with big gaps, big air gaps. I've made a washer 3mm thick, and without changing the focal length, what that's done, that's forced the nozzle down another 3mm. So my setting now is not 7mm but 4mm. So that's 4mm just there, done. We were able to perform this cutting test at 3mm a second with the gallium arsenide 2.5-inch lens. We've now got a 4-inch lens, which I just happen to know, because I've already done this test once before, will not perform it at 3mm a second. So I'm going to have to drop the speed to 2mm a second. I couldn't get it to cut through at 3mm a second at all. What's the difference between a 4-inch lens and a 2.5-inch gallium arsenide lens? Let's take a look. Now, without any sophisticated equipment and without being an optical engineer, what we're seeing is different size reflections. That one there is a 2.5-inch plano convex zinc selenide. That one there is a 2.5-inch gallium arsenide plano convex. That one there is a 4-inch zinc selenide plano convex, and this one here is a zinc selenide meniscus lens, 4-inch. So hang on, these are both 4 inches, but look at the images, they're completely different. So the curvature on the top of that is more than the curvature on that one. That's flatter than that one. This is the one that we used for doing our 26mm oak test just now. And that compares with this one, which we used for doing the 26mm oak test at the beginning. We haven't used that one, but I just put that one in there as an example to show you the difference between a zinc selenide 2.5 inch and a gallium arsenide 2.5 inch. The curvature on this is substantially flatter than the curvature on that one. Look at the difference in the size of the images. And even when you look at this one and compare it, this is a 2.5, and compare it with this 4-inch. This 4-inch is still smaller than that 2.5 inch. In other words, this is flatter than that one. And that one, which is a 4-inch meniscus lens, 4-inch would imply, according to my thoughts, that that would have a much flatter surface than a 2.5 inch. Well, you can clearly see that it hasn't, because this is a smaller image than that one. So this one has got more curvature than that one, even though these are the same materials. But obviously there is something about the geometry of this one, because it's a meniscus lens, that has to be corrected both on the top and the bottom surface. Now, don't get too upset. This is my box of special needs lenses. By virtue of the sorts of experiments that I do, as you can see, I often damage lenses in some way, shape or form. This one has had too much power through it and it just cracked. This one is cracked because it's had too much power through the middle. This one is discoloured in the middle because I think I've probably overstressed that one as well. That one, again, has had too much power and it literally cracked. So this is what happens when you put too much power through a lens. This one, well, I think I accidentally dropped that one, and yeah, it's got a chip out of it. But these are lenses that are already dead. So like a good resurrectionist, I'm going to use this dead item here and put it to further use. What I don't know is, what is it? Well, I can see that it's a CVD plano convex. Check. No, it's a meniscus lens. What I don't know is, what's its focal length? So we'll quickly just pop that in there and drop that into my little fixture. And I can do a quick check and see that that is a 2.5 inch lens. This is an 18mm lens that obviously doesn't fit this 20mm stem. I've taken a standard clamp ring and I've modified it so that it's got an 18mm recess in it. So when I drop my 18mm lens in there, it sits central in the lens tube. I also made some 18mm targets and dropped one of those into the bottom there to make sure that the beam was running central to the lens. So the nozzle set 8mm above the surface, and now we'll just run the quick focus test. Right, we're just going to run a profiling test for this lens. Okay, now with all that power that we've got here, remember the 70% in the middle there, the middle 2mm? If what I'm proposing is correct, and there's a lot happening right down this central axis of the lens, then we should find there is a significant effect if I disrupt it just there. So we've got the lens in there now, and here I've got a 0.5mm drill. And there we are, right in the middle there. We've got a little teeny weeny black spot now. Okay, let's see what damage we've done. Well, we've now changed the blind spot from 0.5 to 0.8mm. And now we've got 1.4mm disruption in the centre. Well, I think I've well and truly messed up the lens now, but let's just see what effect I've had. I've messed it up, but you need to see what I've done. Well, as you can see,
I've managed to put a nice big hole right through the lens, and it's well and truly taken away the central power of the beam. But I'm afraid that in drilling that hole I caused a bit of a problem at the back as well. So not only have I got a hole, I've got something fairly dramatic that's happened as well. And so it's not surprising that the lens doesn't work. When I say it doesn't work, it does work, but not very well. But that in itself is an interesting point. How on earth does it do that? Right, now on the basis of what I've just seen, I've created a very special lens here. Let's just see how this performs. Well, there it is, and there's no depth to those cuts, but as you can see, we have actually marked the surface. So here is my special lens. And I'm afraid to disappoint you, but it's just a piece of 4mm thick acrylic with a 1.4mm hole through the middle to simulate what we've just created with the lens. Was there power escaping through the centre of the lens? Well, obviously not much, because if there was, it would have escaped through that hole and done damage to the material. So the lens is having some effect. The reason why I've used a piece of acrylic is because I know that it is going to absorb 100% of the energy, and it has done so there in the form of a sort of a mode burn on the inside of that piece of material, and the rest of the power has escaped through the hole and done damage to the surface of our test piece. But that leaves me with several problems to think about now. How can a lens that's so badly damaged actually still penetrate material? Where's that power coming from? It's not a very deep hole, but it's a conical hole. It's focused power of some sort. When we look at these results here, I guess many of you guys would say, why don't you give up, Russ? This is a total failure. No, I don't agree with you. Now, it really depends on how you start to analyse these results. Bad results are often good results. Like this one here looks like a bad result. No, it's not a bad result. It's a result that tells us something. It tells us that there is not a lot of power passing through the lens in an unamplified way. Because if it was amplified, I would have depth. So the beam that is escaping through that hole, and it is escaping through that hole because the rest of it is being captured, is so small in its intensity, its natural intensity, that all it can do is damage the surface. Now, on the other hand, despite the serious disruption that that lens must be causing, we're still getting penetration, because that is somehow focusing the light and increasing the intensity and allowing us to get depth. On its own, it doesn't look very interesting. But when we look at the results of what we've achieved so far, the original one, the normal, which is unmodified, is the blue one at the top, and gradually as we modify the lens with a 0.5, 0.8 and then a 1.4 missing centre spot, we are gradually degrading the cutting ability of that lens. So whatever that cutting ability is definitely coming through the central part of the lens. Because here we're affecting it, here we've grossly affected it by putting a hole and doing some damage, and here, when we allow the light through in an unamplified way, we basically get nothing. I don't see this as failure, I see this as making fairly interesting progress. Now, the other thing about this pattern here that's interesting is that I'm using a 2.5-inch meniscus lens. Now, as I described to you earlier, the meniscus lens has got some rather strange geometric properties, which maybe I shouldn't be using for this test. Maybe I should be using a plano convex. Now, I'll have to go and have a look through my rogues gallery to see if I can find a plano convex to run these same tests with, and perhaps if I'm a bit more careful about how I do the machining, I won't finish up with this. Okay, now before we go any further, I've put that well destroyed 2.5-inch meniscus lens back into there, and I'm going to carry out a focus test on it because, hey, we may as well check everything while we've got the opportunity with this wonderful Polo lens. I've taken the centre away. Have I changed the focus? I mean, technically the answer should be no, because most of the focus is coming in from the side and not the centre. I think previously this lens was set at 13mm focus. And we've started off 7mm gap. 8, 9, 10, 11, 12, 13, 14, and it's not a lot thicker than it was before. It's absolutely staggering, isn't it, for such a disreputable lens. So we'll set that focus to 14mm. Okay, so we want it a little bit darker. I can put the power up, and interestingly, power is having no effect on colour, so we need a little bit more burning time, which means we will have to change the step interval from 0.2 back to 0.1. That will burn twice as much. It's actually burning in quite deep. Wow. And if I take that up to 0.3, slight change in colour. I have to say, I've got more control over that lens than I've ever had on an engraving lens before. So, hey, I've just invented the square wheel. Don't laugh. Square wheels have got fantastic properties. You don't need handbrakes. Nobody's going to pinch your car. You're not going to believe that that engraving was done with that crap lens, are you? So look, on camera, no tricks. This is not anything like, this is not David Copperfield or anything. Look, there it is. The nozzle is just very slightly warm, so there's a little bit of power scattering inside there, but I mean, who else in the world is going to show you mad off the wall stuff like this? I find it fascinating. It edges towards my theory of lenses. You know, what's happening on the outside is having nothing to do with the focal point. But we know that that lens will not cut, but it does engrave. Okay, so technically this is what all lens manufacturers are trying to achieve. A very good focus, because I've removed the bit that goes out of focus down the centre. Now, I wouldn't say that I've proved that categorically, but there's some pretty strong evidence to suggest that that lens that was cutting quite nicely with this blue line, and then when we destroyed it, it came down here. So as a cutting lens, it's absolutely useless now, but it's not useless as an engraving lens. I mean, just look how badly damaged that lens really is. Not only have I got a serious chip out of 1/6 of it, I also destroyed the back, and it's got no centre. Maybe lens manufacturers ought to be making Polo lenses for engraving. I've managed to machine another 1.5" lens, marginally better, in that everything is uniform. Look, I've had a crack away at the front there, and the back is not too bad. But again, we're going to use this lens flat side up and see what happens. If we take a look here, I've got a sister lens to it, and this lens has got just a little bit of imperfection on the right on the centre there in the anti-reflective coating. Okay, so this is not a perfect lens, but it obviously appears that lenses don't have to be perfect to work. So we've got two reasonably equivalent lenses there, which we're going to test. So there's the lens in its normal state. Aha! So now we have categorically lost power from the centre of the lens. What's it like as an engraving lens? Well, apart from the smoke filling my workshop, it's even darker. So now we know how to make great engraving lenses. Just drill a hole in the middle. Honestly, I would advise you not to. I think if you do a little bit of reading on this material, you'll find it's very toxic. The only reason you'll see me handling these lenses like this without gloves and that on is because they're coated with a material that protects you from the toxicity of the base material, which is zinc selenide underneath. So I was very careful when I machined these, and yeah, I was wearing a mask, and I was also doing it very slowly, and I didn't blow the dust anywhere. Well, as you can see, it's a lovely day. Spring is in the air. I'm feeling a little bit smug because although I haven't proved that my theory is right, there's a lot of evidence there that says I'm on the right track. So I'm going to leave you and the lens makers a few things to think about after what you seen me do today. I'm going to catch up with you in the next session. So thank you for your time and patience.